So first one, the pressure of a gas is inversely proportional to the volume. So basically, if you write this out, inversely proportional has to be on the same side of the equation, right? That's another way of saying if everything else is constant besides pressure and volume, then you have PV equals well, I don't want to say that. Yes. So if everything else is constant, same moles of gas, same temperature, and I increase the pressure, you have to ask yourself almost like, how do you increase the pressure if you're not increasing the number of moles of gas? Well, you do it by decreasing the volume. That's the only way to increase the pressure, right? If you're not going to add numbers of moles of gas. So they're inversely proportional. So if this were to increase, this has to decrease for it to equal the same value over here, right? That's inversely proportional. Directly would have to be on opposite sides of the equation. So you can ask this about a lot of things. You can say about moles and temperature. They would also be inversely proportional, right? But moles and pressure would be directly proportional. But think about it in terms of what's happening in terms of kinetic molecular theory also. Why does pressure increase when I increase the number of moles of gas? Right, greater force from all the molecules, more collisions, if you want to talk about specifics, more collisions with the walls, right? That is what pressure is, that force per unit area. That's what's defined as pressure. So the molecules are colliding with the cylinder wall, the balloon wall, whatever. So think about gas laws in terms of that also as you study, get down the understanding of temperature. Two things happen when temperature increases that increases the pressure. What are they? Why does the pressure increase when I increase the temperature? Spread out, but that doesn't really answer it.
They have more energy, so they
finish faster. It's faster. They have more energy when they collide, right, against the cylinder walls. But you also have more collisions because they're moving faster. You can have more collisions with the walls. So you have more collisions and you have more energetic collisions. That's why the pressure increases. Make sense? Questions on the first one? All right. Incidentally, no one in my family has been sick for like a year and a half. You know why? I mean, all the sicknesses we get are all transferred from bacteria, viruses in the air. And a lot of cultures wear these things all the time. Not all the time, but during heavy flu season, you know, they all wear them. I think I'm actually continue to wear a mask like heavy flu season, especially if I go to like Walmart. If I go to like a really big festival or something like that with a lot of people I don't know that are breathing and coughing all over me. So I think I'll adopt it. All right. A gas is contained. The gas is contained in the piston. Okay. A gas is contained in the piston assembly. That's not the greatest wording. Anyway, a gas is contained in the piston assembly and allowed to expand as in the following figure. Which point on the graph shows the correct final pressure and volume? D as in David? Agree? Some shaking, some a little certain. So clearly the volume's increasing, so we want to move along here. And since we started, it looks like here, right? Doesn't matter where really exactly. But theoretically, if that looks like, you don't know for certain, it looks like the volume doubled, but we can't be certain about that. But anyway, the volume's got to increase, right? And if the volume increases, the pressure decreases. Why? Well, because they're spread out, more or less collisions with the walls, right? We just talked about this kinetic molecular theory. So it should be D. What wouldn't be fair is the question, the reverse question, where it went down to here, right? Because then you're not sure if it's B or A. It would have to be proportional, but that wouldn't be a fair question for an exam because they both would be increasing pressure and decreasing volume. You just, you know, if there was a huge difference or something, maybe you could be making a fair question where you had, here's the starting point. Well, even that you can't do. You have to be totally proportional. You'd have to have this like marked like a volume, like 10 liters, and mark it, and then it'd be totally proportional. You'd have to have a graph with points to be able to do that. Because if we double the pressure, we should half the volume, right? That's the point I'm trying to make. 4 times the pressure, quarter the volume. So in order to answer a question like that, you'd have to have the gradations on the graph and on the cylinder to know exactly. Okay, questions on that one? All right. A sample of neon gas, 745 torr and 60 liters is compressed. Everybody should have the calculators out because I don't have the answers to these. A sample of neon gas at 745 torr and 60 liters is compressed to 14.5 liters. If the temperature remains constant, what is the final pressure of the gas? How do you want to do this? T1 V2. Well, let's start with PV equals nRT, like I mentioned. But Megan's taken the step and realized already. So what do we have? We've got P equal to 745 torr. V is equal to 60 liters. And then it looks like we've got a second volume. So we can do V1 and V2 is equal to 14.5 liters. So basically it's being compressed, right? It tells us that volume's getting smaller. We expect the pressure to increase. We should expect a P2. That's what we're after. Effectively, what we've said is this is constant, right? That's what we said. Put everything on one side of the equation. You don't have to do any rearranging here. We say PV equals a constant. Therefore, exactly what Megan said, P1 V1 equals P2 V2. And now we can solve it. Everything's in torr, so we don't have to bother converting it to atmospheres, right? We're not multiplying with the ideal gas constant. If we're using the constant, then the units have to be the same as the constant, but the constant's not involved here. It's being canceled out effectively when we derive the Boyle's law there. So we can just say 745 torr times 60 liters. And we're after P2. So I'm going to divide by V2 over here, which is 14.5 liters. That gets rid of my liters. My answers are in torr, which is what I want. And what do I get? C, let's double check. 745. It should increase substantially. I mean, this is like what? 20 roughly, 1/20th of the volume. No, that's not what we're talking about. Fifth. 1/5 of the volume. A little bit less. So pressure increasing by 4 or 5 times. 7 times 4 is 2,800. That makes about sense. You've got about 3,000 torr. Questions? So this one, you didn't have to rearrange anything because P and V are on the same side of the equation. It was Boyle's law. Yes?
So is temperature the only units like you technically have to convert to like in the Kelvin?
So yes, if you're using like Charles' law with volume and temperature, you have to put it into Kelvin. Now, anytime you use the ideal gas law with R, if you're using R, you have to convert everything to those units. But I think what you're asking is if we had something like Charles' law, which is like V1 over T1, T2. So yes. So you have to convert that to Kelvin. That
I mean, like for the ones where temperature is a constant, like you don't have to convert to like pressure. You don't have to convert to atmospheres. You can keep it towards.
No, that's right. Okay, right. That's what we did. Yes, so temperature is constant, like in this one, and we did not convert to atmospheres. That's correct. We do not need to do that because look at your units. Liters cancel out. You're left with torr. Who cares, right? We're good. If we use R, you've got to convert. And if you're gonna, anytime you're gonna use temperature, you always have to convert because it's proportional temperature, specifically to Kelvin. You can't do Charles law or any of these things without converting to Kelvin. But all the others, pressure, volume, you don't have to worry about converting those if you're not using R. Okay? Other questions? All right. A 1.5 mole sample of helium occupies a volume of 2.50 liters at a pressure of 14.7 atmospheres. What will be the pressure if 1.5 mole sample of hydrogen? Yes, under the same conditions. I thought it was a typo. Okay, so we're just asked to basically compare it, and we can just use. We've got hydrogen gas. It's all we care about, right? Doesn't matter. The identity of the gas is irrelevant because ideal gas equation doesn't matter, right? It's hydrogen or helium. Same conditions. So it's just a word problem that makes you think a little bit, but you still have a 1.5 mole sample. So N is 1.50 moles. Of course, I'm going to write PV equals nRT here. Same condition. So that means volume is equal to 2.50 liters. And pressure is equal to 14.7 atmospheres. Oh, they want to know the pressure. Okay. Oh, I see. Okay, so pressure is what we're after. I don't remember this question. Sorry. Not a. Okay, so pressure is what we're after. What will be the pressure? Okay. So basically, we're going to have to figure out what. Because we're not given something here. We have a N and we have V. We can either calculate the temperature, right? Or we can, let's see, we have PVT. So we can calculate the temperature. We also have same conditions, same moles. So moles are constant. So you could use a PV approach also, right? Because you have a pressure and a volume. And then we have a, no, we don't. Never mind, sorry. We have only one volume. Only one volume, one pressure. Yes, so we can't do that. I thought I'd given additional there. So we can't do that. So we just have to do PV equals nRT for helium effectively, right? And we're going to calculate the temperature as Houston said. We have a pressure and a volume, so we're good there. And we have moles, so we'll just solve for temperature. So we'll get T is equal to PV over NR, which is equal to pressure. We've got 14.7 atmospheres. It's a little bit tricky problem because of the wording. It threw me a couple times. Whoops. liters, 1.5 moles. And then R is always going to be given to you 0.0821 liter atmospheres per mole Kelvin. That'll get us temperature, and then we can use that temperature in our hydrogen calculation. So I need that from somebody, that answer there. Two people should do it at least. So we go 14.7 times 2.5 divided by parentheses 1.5 times 0.0821. What is it? 298.6. Anybody else get that? Yeah. Okay. 298.6 Kelvin. Now we can just plug it into helium. And this is the advantage, you know, I didn't see how to do this problem right away, and that's okay. But by writing it out, and I said to myself, oh, I can use Boyle's law because they just want me to do hydrogen at the same. And I realized, oh, no, I don't have two volumes. I don't have two pressure. Can't use Boyle's law, right? What do I have? All I have is one volume okay, one pressure, and I've got the same moles of gas for two different gases. So now I can just figure it out for helium. That's helium. Now I can do hydrogen and just use that temperature because it has the same conditions. So it's asking you to kind of realize that, hey, hydrogen would have the same temperature as helium at the same conditions. And that's what kinetic molecular theory tells us, right? Doesn't matter the identity of the gas, it's going to be under those same conditions. So let's do that now. And we're asked for pressure. So we got pressure is equal to the N is the same, 1.5 moles. R 0.0821. I'm going to drop the units because I'm running out of space here. That's nRT 298.6 K. And then since I'm solving for pressure, I brought the volume over, and my volume is the same too, 2.50 liters. So everything's the same for both gases. We just had to solve for one of the temperatures. So it's a little bit long problem. Surprised I put this on the exam last year, but I always have one or two what I consider my tougher questions for my A students. So what did we get here? B. Boy, who said that? Carter. You got that? Everybody agree with B? 14.7 atmospheres. What is it? Did you figure out another way to do it? Or, it's what? Temperature's in the question? So how would you do it? That's what I started to. Dead.
So if you were to have, like, if this were the same problem, but instead of like H2 gas, you had very dense gas, like a much more dense gas than what that other was. Like, if they have the same number of moles, is the pressure the same always? Does it matter
If the
molar mass?
no, it doesn't. That's the point of the whole kinetic molecular theory. So if here's the equation. If the volume of you just proved it to yourself right here, hydrogen and helium are not the same. You can choose as dense as gas as you want. If the number of moles, the temperature, and the volume are the same, the pressure is the same.
So we don't really need to solve all that.
So I can see what you're saying. Because you're given the pressure. That's why I gave this problem. I said, this is too long. What did I do? I wouldn't. So the pressure is given, so you know that. Yes, thank you. Well, we get good calculation fun exercise. Yes, that's right. Very good, Hershey. Thank you. And who else? Anybody else that was figuring that out? So, right. So we've got the same exact things, and there's your pressure is going to be the same. So that's kind of what you're maybe getting at too.
Yeah, so even though basically if you have 1.5 moles of helium, you have a lot less mass inside.
Yes,
the balloon,
exactly.
it's still the same amount of pressure.
Right. Because the pressure comes from the speed and the energy of the collision. But remember, kinetic energy is 1/2 mv squared. So the mass is greater of the heavier one, but its velocity is less. So the kinetic energy is the same. Very good. So you're thinking, and now as you think these things through, you learn. That's the whole point. We're thinking this through. So now we realize that what Abigail said, you start to realize it from kinetic energy is 1/2 mv squared. And she's asking this question, but wait, shouldn't a more dense gas have more energy? But no, it's slower. So the energy is the same because mass is higher, right? So they cancel each other out. All right. So yeah, we didn't need to do that, but I was like, that was a pretty long question for the exam. All right. In an experiment, hydrogen sulfide gas is collected in a 1.25 liter flask at 210 Celsius, 758 torque. How many grams of H2S are obtained? And we've got the molar mass. What we do here? temperature, the pressure, we got volume. Should be easy enough to get moles, right? And then we can convert to grams because we're given a molar mass which has grams in it. Don't think about what I have to multiply, divide it. We'll just get there and then look at the units. As always. And what do I have? I've got volume, a temperature, a pressure, I need that pressure, 0.9 something, obviously. I did that, yeah. What's that? Thank you. 0.997 atmospheres. Sorry, I squished that atmosphere in there. 0.997 atmospheres. Then this is pretty straightforward. Just solve the n. It's the last step that a lot of students just can't seem to finish the problem. So we're going to have n is equal to PV over RT. Once we arrange that, don't make that silly mistake. $1.25 liters, 0.0821 liter atmospheres per mole Kelvin, and 294 Kelvin. Multiple choice exam using 273 is fine instead of using 273.15. What do we get there? What is it? 0.516 moles. We got someone else get that too, okay?
0.5.
Oh, 0.5, thank you. All right, that's our moles. And the question's asking how many grams? Well, we've been given a molar mass. Just look at your units, right? If I multiply it by my molar mass, the moles will cancel out. I'll be left with grams, right? So just say, okay, 34.08 grams per mole. Sometimes I make that silly mistake too, and I go to divide it or whatever. Just look at your units and it catches it. You get rid of moles, you get grams, and that should be our answer. I have no idea what the answer is, so. 1.760 E. And of course, the 0.0517 grams is up there. So if you stop at the moles and you look and say, oh yeah, there's 0.015516, that's the answer. No. Okay, make sure you finish it. And if you do finish it, then there's no other answer close to that. So maybe 1.36 is the closest. Questions? Okay. Six. What is the temperature if 5 grams of methane in a 100 ml container exerts a pressure of 42 atmospheres? If you practice these enough, they'll start to all kind of look the same. It's like, okay, I just got to convert that to moles. P equals RT. I'll just get rid of that. That's constant, and that's good. It becomes common to you. It becomes redundant. Then you know you're comfortable with it. Okay, so what have I got? I've got a mass. I got a pressure. And I've got a volume, right? And the temperature is what's asked. So I should be able to convert to moles and then use PV equals nRT pretty simply, right? I need the molar mass of methane at 12 and 4 is 16. Okay, so we can use that and just say 5 grams times 16 grams per mole. What do we get there? What is it again?
0.3125.
Moles. And then I can use PV equals nRT again. And I'm asked to solve for temperature. So T is equal to PV over NR, which is 42 atmospheres. Got to convert that to liters, right? I saw a couple of people shaking their heads. Liters, N, we just calculate that. And R. Never silenced my phone, sorry. And then what do we get for 6? Okay, now keep in mind, their temperatures are all in Celsius, so I didn't see that. I didn't even look at the answers. So what do we get for Kelvin first? 163.78. Kelvin, then we got to subtract 273. And then what do we get? A, you said? Is that right?
Yes.
A. So yeah, look at that carefully. I didn't look at the answers. And then we get Kelvin for 163.78 and then minus 273. Questions? All right, here's the density problem. Everybody good on this one? Okay. Was the density of sulfur hexafluoride is still under 1.5 atmospheres per 22 degrees C. I feel like I'm going to need more room, but might just go down here. Okay, so we've got a pressure. .5 atmospheres. Temperature 22 degrees C. What the heck? What am I going to do? I don't have moles. My goodness. How am I going to solve this? I seem like I'm missing something else. I mean, if that PV equals nRT, all I've got is pressure and temperature. Seems like I need volume or moles or something, right? What am I going to do? Asking for density. What do you want to do? What's density? What do you think about when you think about density? Talia? N over V, right? Amount of material over volume. So forget the fact that you don't have, solve for the two unknowns together. Okay, put what you don't know on one side and solve for it. At least go that far, and then you'd be surprised. You say, "Oh, wait a second, look at my unit. Look, I was also given a molar mass, and I've got, then you'll get to the answer. If you just stare at it and say, well, look, he didn't give me enough information. I'm going to do what Talia said and solve for N over V instead of worrying about it. So I'll then have, whoops, P, I'm going to bring the RT over, is equal to N over V, which is equal to P over RT, and I've got P. That didn't sound good. P over RT 0.0821. I'm leaving out the units because I'm getting lazy. And 295K. You do it so many times, you know what the units are, you know, you work on an exam, you get comfortable enough with it. So we're going to be solving for N over V. Maybe I will write it here so we can see it here. Whoops. It's supposed to be a K. Liter atmosphere per mole Kelvin. Okay, so atmospheres cancel out and Kelvin cancel out. And I got 1 over liters over moles, right? So I'll get moles per liter as my answer, my units. And that's what you expect. You got N over V. You expect moles per liter. What do you get for a number? 0.06, that's it? Okay, 62. 0.062 moles per liter, right? Okay, we don't have an answer yet, but now go back and look and see. We have grams per mole. Oh, it's wrong problem, sorry. We have the molar mass, grams per mole right there, right? And they're asking for density. And look at all the units are grams per liter. So we're given grams per mole on top of this. And we have moles per liter, and we want grams per liter, right? So can you see that then? If I take 0.062 moles per liter times, what was the number? 146.1. 146.1 grams per mole. I will get an answer of grams per liter. So always solve for something. The fact that you're solving for 2 unknowns grouped together, who cares? You're effectively solving for N over V, which is kind of a density, right? Material over volume. What do we get for our answer? So B, is that what you got, B? Agree? Okay. Okay, does that make sense? So if you see 2 things missing, then solve for them together. And then look at your units. How many times I could stress that units will help solve a problem when you're lost. Lots of times I've stared at a problem and had not a clue where to start. Then I just kind of look at the units and say, well, okay, this is what I've got. This is where I'm going. If I multiply these, I can get rid of that and get to the, you know, that's the idea of dimensional analysis. All right, we're good with 7. 8. Hydrogen sulfide gas, that's stinky smell, like rotten eggs, landfills, sewer gas. That's what you smell, H2S. Hydrogen sulfide gas can be, they used to make little stink bombs when I was a young kid in glass tubes, and they're filled with this kind of stuff. You could clear auditoriums with them. I won't say that I ever cleared an auditorium. I wouldn't admit to that. All right. Hydrogen sulfide gas, we're given the molar mass, can be produced from the reaction of aluminum sulfide, molar mass given in water, molar mass given according to the following equation. So we're given the balanced equation. Aluminum sulfide plus 6 waters gives us 3 of the gas plus aluminum hydroxide. So you're forming an insoluble precipitate. There's your aluminum hydroxide, right? So you know this is a reaction. You're forming a gas also. All right. We've got 65 grams of this aluminum sulfide. Excess water, we need to worry about that. We got a temperature, pressure. The question is, what volume of gas will be produced? What do I do? This is what we're after, the volume of this. Right, use stoichiometry to figure out, use chapter 7, I guess that is, right? Figure out how many moles of hydrogen sulfide are produced. Then you have a gas, and you just do the ideal gas equation, like we always do, right? That's all. Mass, right? Mass of A to moles of A, moles of A to moles of B. And then you can stop. You don't need to go to mass. So we've got this. Where is it? 65 grams. There it is. All right. So I'll do that over here. I'm not going to have enough room. 65 grams. I'm not going to have enough room. I'm going to do it down here. Al2S3 times, and we've got the molar mass. We were given that, right? Aluminum sulfide, 150. That's mass of A to moles of A. Then use my stoichiometry. Use what you're trying to find, the 3H2S for every 1 of the aluminum sulfide. These are moles. And that's all we have to do for that part. We got rid of the grams of aluminum sulfide. We got rid of the moles of the aluminum sulfide. We now have moles of hydrogen gas. What do we get for an answer? Okay, and that's moles of H2S. Then all it's asking, hydrogen sulfide gas can be reduced from the reaction, water according to the following reaction. What volume? That's what I want, the volume. But of course, I'm going to use PV equals nRT. So I'm going to just get nRT over P, which should give you my answer. So 1.2983 moles. 0.0821. I'm leaving the units out there because I'm going to run out of space. You need nRT. What was my temperature? Oh, 90 degrees C. So what's that? 363? 363 Kelvin. And I never wrote it here, but we got pressure, right? We're solving for what again? Volume. Okay, so we've got volume is nRT over P. Pressure in the denominator is 0.987. And that's the equation to solve it. Which one do we get? A, as in Albert, 39.2 liters. It's a decent amount of math on this exam, but it's a little bit plug and chug. Whereas some of the math we've done before, it's not so straightforward here. It's like you got this one equation you use a lot, right? It just reduces to different forms, and you have different things you're solving for. Sometimes you got to convert temperature or pressure to the proper units, but enough practice, not too bad. Got one left, 9. What is the any questions on 8? Good. What is the mole fraction of O2 gas, O2 in a gas mixture with a total pressure of 750 torr when the partial pressure of O2 is 125 torr? Really, if you know you know what Dalton's law of partial pressure is. It is as easy as it looks. What do I do? 125 over 750. That's all it is. Just that you realize that the mole fraction is proportional to the pressures. So that's all it is. That's the partial pressure of O2. So that will be the equivalent fraction of its mole fraction. So it's just 125 torr over 750 torr. Now read the question carefully. Sometimes there'll be two gases, and I've done this in the past where I have got two gases, and I give you the total pressure. Let's do it right here. First of all, what's the answer to this one? Now here's an example of another one. Everybody good with this one? Okay, I've got two gases in a mixture, and I've got oxygen, and I've got hydrogen. Okay, and I've got a total pressure equal to 800 torr, and I've got a partial pressure of hydrogen of 100 and let's just say 200 torr. My question is, what's the mole fraction of O2? You shouldn't need a calculator. Put your calculator. What's the mole fraction? 3/4, right? 2, 4, 6, 8, and we've got 6. So a mole fraction is 600 torr over 800 torr, which equals 0.75. People read that, they go quickly and say 200 over 800 and get the wrong answer. And of course, that's going to be one of your choices. Don't zip up so quick. I will go over the outline, at least for chapter 9. It's early. I'm not going to start the material, but yes, Mary. So if the total pressure is 800 and there's only two gases and hydrogen's 200, well, 800 minus 200, oxygen must be 600.
Oh, you're right.
And then it's the part over the whole for any fraction or percent, however it's asked, part over the whole. In this case, it was asked for oxygen, so it's 600 divided by 800.